Welcome to this channel. I am Omotola Fayomi, and in the next few minutes, you are going to completely master industrial chemistry for your JAMB examination. Industrial chemistry is one of the highest yield topic in JAMB chemistry. Question on Haber process and counter process, Solvay process, blast furnace, and electrolysis of brine appear in nearly every JAMB paper. The key: every industrial process has a specific purpose, specific equations, specific conditions, and specific why for each condition. We will cover the Haber process, counter process, Solvay process, blast furnace, chlor-alkali process, aluminum extraction, Oswald process, fertilizer production, and the grand comparison table, all in these few focused minutes. Let us go. We begin with the Haber process, arguably the most important chemical process in human history. Without the Haber process, we could not produce enough fertilizer to feed the world's population. It is estimated that over 8 billion people alive today exist because of the food grown using derived fertilizer. The Haber process is the industrial manufacture of ammonia from nitrogen gas and hydrogen gas. The equation is N2 nitrogen plus 3H2, that's hydrogen, to give 2 moles of ammonia. The double arrow tells us it is a reversible equilibrium reaction. The delta H is minus 92 kJ per mole. The forward reaction is exothermic, releasing heat. The starting materials: nitrogen comes from the fractional distillation of liquefied air. Air is 78% nitrogen. It is all around us. Hydrogen comes from steam reforming of natural gas methane, plus steam at 900 degrees Celsius with a nickel catalyst gives CO, carbon monoxide, and hydrogen. The carbon monoxide is then converted to more hydrogen by the water-gas shift reaction. The ammonia produced has remarkable range of uses. It goes directly into fertilizer, that's ammonium nitrate, urea, ammonium sulfate. It becomes nitric acid through the Oswald process, and it is used to make explosive nylon fibers and also cleaning agents. The conditions of the Haber process are where JAMB scores the most mark, and every single condition has a reason rooted in the Chatelain's principle and industrial economics. Let us master them all. Temperature: the forward reaction is exothermic. The Chatelain tells us lower temperature shifts equilibrium towards more ammonia, favors the exothermic direction. So lower temperature gives more ammonia, better yield. But here is the industrial reality: too low a temperature means the rate of reaction becomes impossibly slow. The reaction will take years to reach equilibrium at room temperature. So the industrial compromise is 450 degrees Celsius, fast enough rate, acceptable yield. This is the thermodynamics versus kinetic balance. What about pressure? The above equation has 4 moles of gas on the left, that's 1 nitrogen plus 3 moles of hydrogen, and only 2 moles on the right, that's 2 moles of ammonia. The Chatelain says that higher pressure shifts to the side with fewer moles. That is the right side. So higher pressure gives more ammonia. The industrial compromise is that at 200 atmosphere, significantly higher than atmospheric pressure, it gives a good yield, but not so extreme that the equipment cost and safety risks become prohibitive. What about catalyst? The catalyst here is iron with promoters, aluminum oxide and potassium oxide that are used. The catalyst does not change the equilibrium position or value or the value of Kc. It only increases the rate at which equilibrium is reached. It is essential for economic viability. At 450 degrees Celsius, ammonia removal, which one can carry out. Ammonia removal is what about ammonia? What about ammonia removal? Ammonia is continuously liquefied. That's boiling point at minus 33 degrees Celsius and removed from the equilibrium. By Chatelain, the removing of a product shifts the equilibrium forward, producing more ammonia. The unreacted nitrogen and hydrogen, about 85% of those gases, are recycled back into the reactor. This is excellent green chemistry. The counter process manufactures sulfuric acid, the most produced industrial chemical in the world by volume. The quantity of H2SO4 a nation produces is historically used as an indicator of its industrial development. Sulfuric acid has an extraordinary range of uses, making fertilizers by far its biggest use, converting soluble phosphate rocks to soluble superphosphate, car batteries, synthetic detergents, petroleum refining, dyes, and paints. The counter process has 4 distinct steps. Step 1 is to burn sulfur in air, that's oxygen, to produce sulfur dioxide. That's SO3 is also obtained by roasting metal sulfide or like iron pyrite, that's FeS2. Then step 2 is that this is the key equilibrium step. The step 2 is the key equilibrium step that gives the process its industrial challenge. The 2 moles of SO2, that's sulfur dioxide, plus oxygen gives 2 moles of SO3, that's sulfur 6 oxide or sulfur trioxide. This is a reversible equilibrium reaction, exothermic, with 3 moles of gas on the left and 2 moles on the right. Catalyst is vanadium pentoxide, temperature 450 degrees Celsius. The SO3 produced cannot be absorbed directly into water. This creates a dangerous corrosive acid mist that cannot be condensed and collected. Instead, SO3 is absorbed into concentrated 98% sulfuric acid to form oleum, also called fuming sulfuric acid, or H2S2O7. Step 4, the oleum is then carefully diluted with the calculated amount of water to produce the desired concentration of sulfuric acid. This way, no mist forms and the reaction is controlled safely. Now let us analyze the conditions of the contact process and critically spot the key differences from the Haber process. Temperature, same logic as Haber. The forward reaction is exothermic minus 197 kJ per mole. Lower temperature gives more SO3 thermodynamically, but too low means too slow kinetically. Industrial compromise here is 150 degrees Celsius, same as Haber, not a coincidence, same logic. What about pressure? Here is where contact and Haber differ dramatically. For contact, there are 3 moles of gas on the left and 2 on the right. Higher pressure should give more SO3 by Le Chatelier, but contact process achieve 99.5% conversion at near atmospheric pressure, where excess oxygen is used. So high pressure is economically unnecessary, unlike the Haber process. Catalyst vanadium pentoxide at 450 degrees Celsius. This is one of the most commonly tested JAMB facts. Students sometimes write iron, which is the Haber catalyst. Contact is V2O5, that vanadium pentoxide. Never confuse them. Excess oxygen using here in excess ensures that SO2 is not wasted and that the equilibrium is pushed forward by Le Chatelier, maximizing SO3 production. This is why 99.5% yield is achieved without high pressure. The excess oxygen acts as the driving force. The Solvay process is the industrial manufacture of sodium carbonate, also called soda ash or washing soda. It is one of the most elegant industrial processes ever designed, and JAMB tests it regularly. The raw materials are simple and cheap. Salt, that's in sodium chloride, from brine, limestone, that's calcium carbonate, and ammonia, which is itself recycled and recovered in the process. The clever chemistry is in how these inexpensive materials produce the valuable sodium carbonate products. Step 1, concentrated brine, that's salt solution, is saturated with ammonia gas to create ammoniated brine. The ammonia makes the solution alkaline, which is essential for the next step. With step 2, carbon dioxide gas is then bubbled through the ammoniated brine. The carbon dioxide reacts with the sodium ion, ammonia, and water to produce sodium hydrogen carbonate, which precipitate out of solution because it is the least soluble of all salt present. The key equation NaCl plus Na3 plus CO2 plus H2O gives sodium hydrogen carbonate, which precipitate, plus ammonium chloride, which stays in solution. Step 3, the sodium hydrogen carbonate precipitate is filtered off and heated. Heating decomposes it. 2NHHCO3 gives Na2CO3 plus water vapor plus CO2. The CO2 is recycled back to step 2, minimizing waste. Step 4 is that the limestone is heated. Calcium carbonate gives CaO, calcium oxide, plus CO2, providing the carbon dioxide for step 2. The calcium oxide reacts with water to give calcium hydroxide, slaked lime, and this calcium hydroxide reacts with ammonium chloride from step 2 to release ammonia for recycling, and this gives calcium chloride, ammonia, and 2 moles of water. Uses of sodium carbonate. This sodium carbonate is used in glass manufacturing, which reacts with sand and limestone, for paper making, for soap production, for water softening that removes calcium ion and magnesium ion from the hardness, add water and as washing soda in laundry. The blast furnace is the most important industrial process for extracting iron from its ore, and JAMB tests virtually every detail about it. The blast furnace charges what is put in at the top. Iron ore, that's amethyte, iron 3 oxide, Fe2O3, coke, a form of carbon, provides the reducing agent and fuel, and limestone, that's CaCO3, serve a crucial role we will discuss. Hot air is blasted in through nozzle at the bottom, creating very high temperatures. The reaction is that first, coke burns in the hottest zone, that C plus O2 gives CO2. Second, and this is the most important reaction for JAMB, the CO2 rises and reacts with more coke, that's more carbon, CO2 plus C to give carbon monoxide, CO. This carbon monoxide is the actual reducing agent that reduces the iron ore. Students often say coke reduces the iron, but the real reducer is the CO. The main reductions, Fe2O3 plus C3CO gives 2Fe plus 3CO2. The iron is produced as a molten liquid and sinks to the bottom of the furnace where it tapped off. Limestone role is that this limestone calcium carbonate decomposes to give calcium oxide and CO2, carbon dioxide. The calcium oxide is a base that reacts with the acidic silica, that's SiO2 impurity from the iron ore. That CaO plus SiO2 gives calcium silicate, that's the slag. The slag floats on top of the denser molten iron and is tapped off separately through a different outlet. The iron produced, pig iron, contains about 4% carbon impurity, which makes it brittle. This is further processed in a basic oxygen furnace to make steel by reducing the carbon content. The chlor-alkali process is a beautiful example of industrial efficiency. One electrolysis process produces 3 enormously valuable chemicals simultaneously. The electrolyte is brine, a concentrated solution of sodium chloride. When an electric current is passed through it using a membrane cell, 3 separate products are collected at the anode, that's positive electrode. Chloride ions are selectively discharged in concentrated solution. Chloride ion gives chlorine gas plus 2 electrons. Chlorine gas is collected above the anode, and that is used to make PVC, plastic, household and industrial bleach, hydrochloric acid, and water disinfection. At the cathode, negative electrode, water molecules are reduced. Sodium ion are not discharged because they are very high in electrochemical series, making them very difficult to reduce in aqueous solution. 2H2O plus 2 electrons gives hydrogen gas plus hydroxide ion. Hydrogen is collected above the cathode, and hydrogen is used as fuel cells as feedstock for herbal process, making ammonia, and for hydrogenating vegetable oils to make margarine. In the solution now, as chloride ion are removed at the anode and hydrogen ions are removed and hydrogen ions are consumed at the cathode, the remaining Na plus and OH minus ions combine to form sodium hydroxide, which is used in making soap and detergents, paper manufacturing, aluminum extraction, and cleaning agent. The membrane cell is essential. The selective ion exchange membrane allows sodium ions to pass, but not chloride ion or hydroxide ions. This prevents chlorine from mixing with sodium hydroxide. Otherwise, they would react to form sodium hypochlorite. That's the bleach, which is a different product altogether. Now, aluminum cannot be extracted by chemical reduction like iron in the blast furnace because it is too reactive and too high in the electrochemical series. Instead, it requires electrolysis. That's the en route process. The ore is bauxite, hydrated aluminum oxide. That's the Al2O3.XH2O. The ore is first purified to alumina Al2O3 by the Bayer process. Here is the key challenge: aluminum melts at 2050 degrees Celsius. Impossibly high to maintain industrially. The breakthrough is that dissolving alumina in molten cryolite, that's sodium aluminum fluoride, Na3AlFC, which lowers the operating temperature to about 950 degrees Celsius. This makes the process economically viable. At the cathode, aluminum ions gain 3 electrons and are reduced to liquid aluminum metal. Aluminum ion gives Al. The liquid aluminum is denser than the melt and sinks to the bottom of the cell, where it is periodically tapped off. At the anode, oxide ions are oxidized to oxygen gas. That's the 2 moles of O2 minus gives O2 plus 4 electrons. The oxygen generated at 950 degrees Celsius immediately burns the carbon anodes, converting them to CO2. This means the carbon anodes must be regularly replaced, adding significantly to the operating cost. This is a key JAMB details. Take note. Aluminum extraction is enormously energy intensive, which is why it is nicknamed solid electricity. However, recycling aluminum uses only about 5% of the energy needed for primary extraction from the ore, making aluminum recycling one of the most energy efficient and environmentally important recycling operations. This is your ultimate revision table, the grand comparison of all industrial processes. Master this table and you can answer any JAMB industrial chemistry question. Temperature pattern is that ABBA and contact both use 450 degrees Celsius, same reason, same compromise, but every other process uses different temperatures. Blast furnace at about 1500 degrees, oil herald at 950 degrees, solvay at moderate temperature, chloralkali at room temperature. Pressure pattern is that ABBA needs 200 atmospheres, significant because 15% conversion per pass. Contact uses only 1 to 2 atmosphere, already 99.5% yield with excess. All others use atmospheric pressure. This is the biggest trap JAMB sets students assume. Contact needs high pressure like ABBA. It does not. Catalyst pattern is that ABBA uses iron, contact uses vanadium penta. Oswald uses platinum, rhodium, solvay, blast furnace, and chloralkali use no catalyst. Oil herald uses cryolite, but is not a catalyst but a solvent to enable electrolysis. Equation N2 plus H3H2 gives 2Na3. That's ABBA. For contact is SO2 plus O2 to give 2SO3. That's contact key step. NaCl plus NH3C plus CO2 plus A2O gives NaHCO3 precipitate. Solvay key step. What about blast furnace key step is Fe2O3 plus 3CO gives Fe 2Fe plus 3CO2, and 2Cl minus gives Cl2 plus 2E minus. That's chloralkali anode. That's the key equation for that particular chemistry. Al3 plus 3E minus gives Al. That's aluminium. For oil herald cathode, write all 6 equations down as your revision priority. The Oswald process converts ammonia made by ABBA process into nitric acid. These two processes are directly connected and together supply the world's demand for nitrogen-based chemicals. Step 1 is that the most important and most JAMB tested step. Ammonia is catalytically oxidized. That's from ammonia NH 4NH3 plus 5O2 gives 4NO. NO is nitric oxide plus 6H2O. The catalyst is a gas of palladium rhodium alloy, PT/RH. Temperature is 900 degrees Celsius. This is very hot. The platinum rhodium gas glows red hot in operation. This step is critical. A less efficient catalyst would make the entire process uneconomical. Step 2 is that the nitric oxide produced is further oxidized in excess air. No catalyst needed. 2NO plus O2 gives 2NO2. Nitrogen dioxide, a brown gas. This happens spontaneously at lower temperature. The step 3 is that the nitrogen dioxide is absorbed in water in the presence of more oxygen. 4NO2 plus O2 plus 2H2O gives 4HNO3. This produces nitric acid solution of about 68% concentration. Higher concentrations that fuming nitric acid require further processing. The largest use is making ammonium nitrate fertilizer. HNO3 plus NH3 gives ammonium nitrate, that's NH4 or NO3. Also used to make explosive TNT, RDX, dynamite by nitration of organic compounds, synthetic dyes, and in pharmaceutical manufacturing. Now, the fertilizer industry is the ultimate application of industrial chemistry, connecting ABBA process, Oswald process, and contact process into a coherent system that fits the world. JAMB tests fertilizer chemistry consistently. Ammonium nitrate made by simply neutralizing ammonia from herbal with nitric acid from household, that's Na3 plus HNO3 gives NH4NO3. Nitrogen content is 35% high because both the ammonium group and the nitrate group contain nitrogen. It is most widely used solid nitrogen fertilizer worldwide. Urea made by reacting ammonia with carbon dioxide under pressure, that's a 2Na3 plus CO2 gives urea, that which is CO into bracket NH2 plus water. Urea has the highest nitrogen content of any common solid fertilizer, that's 46%. It is also used to make urea formaldehyde, plastic and resins. Ammonium sulfate, what about that? From ammonia plus sulfuric acid from contact process, 2Na3 plus H2SO4 gives ammonium sulfate, that's NH4 into bracket 2 SO4. Nitrogen content is 21%, makes soil slightly acidic, which can be beneficial for crops like tea and blueberry. Out of superphosphate made by treating rock phosphate insoluble calcium phosphate with sulfuric acid from the contact process. The insoluble phosphate becomes soluble calcium hydrogen dihydrogen phosphate, which plants can absorb. The percentage nitrogen calculation for JAMB, percentage nitrogen equals mass of nitrogen in formula over molar mass of fertilizer times 100. For urea CONH2, the molar mass equals 60, N equals 2 times 14 equals 28. So percentage equals 28 divided by 60 times 100, that's 46.7%. For NH4, for ammonium nitrate, the molar mass 80, nitrogen 2 times 14 equals 28. Percentage nitrogen is 28 over 80 times 100, that's 35%. Practice this calculation. Here is your complete industrial chemistry cheat code. Every key fact is consolidated for JAMB examination. About N2 plus 3H2 reversible 2NH3 ion catalyst 450 degrees Celsius 200 atmospheres delta AH minus 92 kJ per mole, about 15% yield per pass. Unreacted gases are recycled, ammonia liquefied and removed. Contact process, that's a 2SO2 plus O2 reversible 2SO3 vanadium pentoxide catalyst 450 degrees Celsius 1 to 2 atmospheres, not 200 atmospheres. SO3 absorbed in oleum, not water, 99% yield. What about solvate? That's sodium chloride plus Na3 plus CO2 plus H2O gives NaHCO3 precipitate. Heat the NaHCO3 to get Na2CO3. Ammonia is recycled. The byproduct here is calcium chloride. What about the blast furnace? Fe2O3 plus C plus 3 Fe2O3 plus 3CO gives Fe plus 3CO2. Main reducing agent is CO, that's carbon monoxide. Limestone removes silica impurity as slag. CaO plus SiO2 gives calcium silicate, that's CaSiO3. What about chloralkali? Anode gives chlorine gas, cathode gives hydrogen gas, solution gives sodium hydroxide. Membrane cell keeps products separate. Catalyst match. Learn this perfectly. Aba equals iron, contact equals vanadium pentoxide, oxide equals palladium, platinum, rhodium, gas. Hydrogenation equals nickel. The biggest trap, contact pressure is 1 to 2 atmosphere, not 200 like Aba. SO3 is absorbed in oleum, never in water directly. Blast furnace main reducer is CO, not coke. Urea has 46% nitrogen, the highest, not ammonium nitrate. Now, these 6 power tips covering the most subtle and frequently tested details in JAMB industrial chemistry. 1. The herbal yield of 15% per pass is not an engineering failure. It is the optimal economic choice given the rate yield compromise. The unreacted gases are completely recycled, making the overall process atom efficient. This is cited as an early example of green industrial chemistry. Number 2 is that in contact process, using excess air, oxygen drives the equilibrium forward through the fertilizers. This is why 99.5% conversion is achieved at 1 to 2 atmospheres. No need for the expensive high pressure equipment of the herbal process. Number 3 is that in Solvay process, sodium hydrogen carbonate precipitates out because of its relatively low solubility compared to the other salts in solution, sodium chloride and ammonium chloride. This selective precipitation is the key separation step that makes the process economically viable. But the fourth one, in the blast furnace, limestone does not act as reducing agent. Its role is as a flux. Calcium carbonate decomposes to calcium oxide, which reacts with acidic silica impurities to form the slag that can be separated from the iron. Students who say limestone is a reducing agent lose the mark. Number 5 is that the membrane cell in chloralkali is essential. Without it, chlorine and sodium hydroxide would mix and react to form sodium hypochlorite, bleach. This is a different and less valuable product. The membrane ensures each product is collected pure. Number 6 is that recycling aluminium requires only 5% of the energy needed to extract aluminium from bauxite by the en route process. This makes aluminium recycling one of the most energy saving and CO2 reducing industrial activities possible. If JAMB favorite discussion question. Crucial exam skill applying the fertilizers principle to explain every industrial condition. Let us consolidate the logic for both ABA and contact. The pattern is identical. The forward reaction is exothermic. Lower temperature thermodynamically favors more product, but lower temperature means lower rate. Kinetically, the reaction takes too long. The compromise of 450 degrees Celsius balances these competing demands. Both reactions also have fewer moles of gas on the right. Higher pressure would thermodynamically drive more product, but ABA needs 200 atmosphere because of 15% per pass. Yield justify the pressure investment. Contact achieve 99.5%, as I've been saying, at 1 atmosphere using excess oxygen as the driver, making high pressure economically unjustifiable. The universal industrial logic is that every industrial condition represents a three-way compromise between thermodynamic yield, kinetic rate, and economic cost. When JAMB asks you to explain a condition structure, your answer, the fertilizer tells us X would give more product, but Y, rate, cost, limits this. So the compromise is Z. This framework earns full mark every time. Now, within these few seconds, your non-negotiable industrial chemistry facts. Just listen. ABA ion catalyst, 450 degrees, 200 atmosphere, 15% yield. Recycled contact V2O5, 450 degrees, 1 atmosphere, oleum absorption, 99.5% yield. Oswald platinum rhodium, 900 degrees, brine plus ammonia plus CO2 gives NaHCO free precipitate heated to sodium carbonate, ammonia recycled, blast furnace. CO is the main reducer. CaO plus SiO2 gives slag. Urea has 46% nitrogen, the highest. Ammonium nitrate has 35%. Note that chloralkali gives 3 products: chlorine at the anode, hydrogen at the cathode, sodium hydroxide in solution. You know it all. Every equation, every condition, every catalyst, every product. Your JAMB industrial chemistry grade is A. It is production ready. Outstanding. You have just completed this few minutes masterclass in industrial chemistry. You now know the ABA process with all 5 conditions and their reasons, the contact process, 4-step flow, and why near atmospheric pressure is used, the Solvay process with its elegant ammonia recycling, the blast furnace reactions with CO as the key reducing agent, the chloralkali process, and why the membrane cell is essential, the whole en route process for aluminum extraction, and why recycling matters, the Oswald process, 3 steps conversion of ammonia to nitric acid, fertilizer production, and percentage nitrogen calculations, and the grand comparison table of all industrial processes. That is the complete JAMB industrial chemistry syllabus. If this video helped you today, and I know it has, please like it, share it with every chemistry student writing JAMB, and subscribe to this particular channel for more rapid revision walkthrough and some other on every topic and some other things. Comment below which process do you find most interesting: the elegance of Solvay, the power of the ABA, and the 3-in-1 beauty of chloralkali. Remember, you are not born just to pass JAMB. You are born to excel in chemistry, in your career, in your faith, in your life, That is the mission of this channel. God bless you. Your A grade is production ready. I will see you in the next video. More. Cheers.